In our last lesson, we took a look at the Bohr model of the atom, and we saw that it helps us understand how light interacts with the atom. When an electron absorbs light, it actually moves farther from the nucleus. And when an electron moves closer to the nucleus, it turns out to emit light. But just what colors of light do this? In this lesson, we're going to take a look at the energy of the light particle that causes these transitions in the atom. And then in the next lesson, we'll calculate the frequency and wavelength of that light particle. Let's take a look. Remember that the Bohr model of the atom tells us our electrons are in fixed rings around the nucleus. That's what we see right here. And that we give each of those rings a number to name it. So that's the n equals 1 level. Those rings get closer and closer together as we go higher and higher in energy. And sometimes it's nice to draw those rings in a circle around the nucleus because that's the way the electrons actually move. But when we're thinking about energy in this video, we're going to lay it out like you see here on the right, with the first floor being drawn right here. And on the y-axis, that is the vertical axis of our chart, we have the energy. So the bigger the gap there is between those different floors, the more energy there is. It's actually really useful to just think of this as a building where the first to second floor is a huge jump, and the second to third floor is a smaller jump, and the third to fourth floor is a smaller jump still. Okay, so every time we go up in energy, our gaps get smaller and smaller and smaller. And what we want to think about is how much energy is involved in each of these transitions. So we're going to learn to calculate that energy throughout the course of this video. First, let's think about it qualitatively. Okay, so when we have emission, remember that our electrons are dropping. So say we have an emission that goes from the n equals 4 to the n equals 1 level. Okay, well that means we start right here and we drop all the way down to our n equals 1 level. Okay, or alternatively, say we have the n equals 2 to the n equals 1 level. So there we would have our electrons start at the n equals 2 level and drop down again to the n equals 1 level. Which one of those would be higher in energy? Well, dropping from the fourth story of a building would give a ball greater speed, for example. And so dropping from a higher height gives us greater energy. And what that means is our blue transition here would have higher energy. And as we've seen, there's a relationship between energy and frequency. We actually learned that during the photoelectric effect discussion. And so actually this light emitted during the blue drop, the drop from 4 to 1, would have a higher frequency. We'll learn to calculate both of those in just a second. The same thing basically applies if we think about absorption. That is climbing up to higher floors, right? So our electron, in this case, is going to start out on the ground floor. And let's say we have a transition that goes from n equals 1 to n equals 3. All right, so our electron starts out here, and then we hit it with some light, and that light makes our electron go way up to the n equals 3 level. Okay, and it ends up right there. We could compare that to another transition where we have n equals 2 going to n equals 3. In this case, we start here, and we go up to that point right there. Okay, which one of those jumps is going to take more energy? Clearly going from the first level to the third level. And so once again, that blue transition here is higher in energy. So that takes more energy. And we'll see that it takes a photon or a bit of light with a greater frequency. We could also transition the electron from the n equals 2 to the n equals 3 levels, but that would take less energy. Okay, let's take a look at the equation that's going to help us calculate this. This looks like a lot, and there is a fair amount going on here, but don't worry, we're going to go through it slowly, step by step, and by the end, it won't seem hard. This equation tells us the energy of the photon. And remember, a photon is like a little light packet. We learned during the photoelectric effect discussion that our light can behave as a wave or a particle. And in this case, we're thinking about how much energy would a little packet of light need to kick an electron from one level to another. And we basically just multiply this constant, so that's just a number in scientific notation, by this difference here. In each case, we take the starting n and we plug it in right here. So say we went from n equals 1 to n equals 4. Well, then we would plug in a 1 to that first one and a 4 right here, and we square it. So that 2 there is telling us to square it. Okay, and we take the difference between those two. When we do all of that, we'll get out the energy. Just one note here, this equation actually is just for hydrogen. The math gets more complicated as we get to other atoms, and we're just going to take a look at hydrogen so we can get an idea for what that looks like. Okay, let's go ahead and use this equation. This problem says a hydrogen atom emits a photon as an electron drops from the n equals 3 to the n equals 1 level. Okay, first let's draw that on our little chart. So we're starting at the n equals 3 level, and we're dropping to the n equals 1 level. So this is going to be an emission process. Light's going to be made. Now here is one note that you'll see by the end of this problem, is this equation up here, it's going to give us a negative answer whenever we have an emission process. So if I get a negative number out of there, that's telling me that light has been emitted. Basically, this is speaking from the perspective of the atom, which lost energy as a photon went out from it. So it's counting it as a negative. In practice, we can just ignore this negative, or just keep in mind that the negative means that the light is emitted, whereas a positive means that a light is absorbed. And we'll see both of those options as we go through in the video. Okay, so now let's actually try to calculate our value here. Let's again start by writing all the things we know. We know it starts at the n equals 3 level. So that means our starting n1, is equal to 3. We know that it ends up, that is our second n value, at n equals 1. And we know we're looking for energy. Okay, so now I can plug that into my equation. And let's do that here. We'll have energy equals 2.179 times 10 to the minus 18. And then we're going to have our open parentheses, 1 over, I'm just copying down this equation now, and I'm going to plug in n1 into this first n here. So n1 is 3, and we know we square that. And then I subtract from that 1 over 1 squared. Let me simplify that just a little bit. Energy equals 2.179 times 10 to the minus 18. And then 1 over 3 squared is 1 over 9 minus 1 over 1 squared, which is just 1 over 1. Okay, so what's 1/9 minus 1? You can do this part separately in your calculator by doing 1 divided by 9 and then subtracting 1. And that will give you out a decimal. Or we can think about it in terms of fractions. So we're going to get 2.179 times 10 to the minus 18th. And if I take 1/9 and I subtract 1, remember that 1 is really like 9/9. So 1/9 minus 9/9 is going to give me negative 8/9. This is where that negative number comes from in our answer, because we're subtracting the starting from the final. When we get a negative number, that means that what happened to our n value is that it dropped. Okay, and then we can plug this into our calculator to get out the energy of our photon. All I'm going to do in my calculator is plug in 2.179 times 10 to the minus 18th times, open parentheses, negative 8 over 9. You could also, if you wanted, just plug this whole thing in your calculator, as long as you're careful putting it in. What I really recommend you do is grab your calculator right now. If you don't have one, pause the video, go get a calculator, make sure you get the right thing. Because this little area right here can cause lots of problems for students if they don't put it in their calculator slowly and clearly. That's why I kind of simplified it here on the screen. So work through that a few times until you get the right answer out of your calculator. So what answer should you be getting? The answer you should get is 1.9 times 10 to the minus 18th. We still have that negative sign there, which means that it's an emission process, and the units are joules. And that's always the unit for energy we get out of this equation. It's always going to be joules, which is one measurement for energy. We'll talk about other units which measure energy later in this class. Okay, let's take a look at another problem. This problem says a hydrogen atom absorbs a photon and an electron is excited from the n equals 1 to the n equals 4 level. Okay, So we know that our starting N is 1, our final N is 4, and now we're looking for, once again, our energy. Okay, well, let's go ahead and plug that into our equation. Energy equals 2.179 times 10 to the minus 18th. And then we do 1 over our starting N squared, which is 1 squared, minus, I'm sorry, not 16 yet. We'll get 16 in just a second, minus our final N, 4 squared. And now when we simplify this, we'll still get our 2.179 times 10 to the minus 19th. And we'll subtract 1 over 1, which is just 1, minus 1 over 16, because 4 squared is 16. That means that we should get energy equals 2.179 times 10 to the minus 19th. And 1 over 1 is really 16th over 16. And so that's going to give me 15 sixteenths left. Okay? And so what energy do I get? I get a positive 2 times 10 to the minus 18th joules. Hey, hey.